Hello everyone, welcome back. This is the second lecture of Ordinary Differential Equations course. To begin with, where we left from in the first lecture. So let's try to have a simple task. Now, the task is none other than exactly this is what we uh, mentioned in the first lesson. So other than working with differential equations like equations, something to solve for without knowing where they're coming from, what we're trying to do is to prepare the background for that. So in other words, we're trying to prepare a playfield for dynamical patterns. So that is exactly the task here. So we briefly mention it. Now, you may recall exactly what we did in the previous lecture also, but just to have a quick recap, we had the introduction and then we talked about, like, very briefly towards the end of that lesson, we talked about the construction of this dynamics, like the construction of this play field. I'm just using a very generic terminology here, like let's call it a play field. So we try to prepare it, and I mean we try to do that, and by the end, like I just had like one result, like with a proof. But now let's make it formal. Now let's have this conversation. There will be a little bit of an overlap from that conversation and more formal presentation of that material too, so that we can have a smooth conversation. So the basic setup requires, now what are we trying to do? We are trying to prepare uh, some kind of a mathematical framework to describe dynamics, right? So for that case, first of all, we need to have a time variable. If dynamics, I mean, if we have dynamics, that simply means there is a time variable that would change things around, or that would be the underlying variable uh, of the change. And then the second component is going to be where we are going to see this change, where we are going to see the dynamics. So that's exactly what we are seeing here. The first one is the time set. Now, in the previous conversation I gave you last lecture, I mentioned like this time set can be um, indicated by a generic or like a uh, general notation by calling it just t, where we can replace it when we need it to be replaced by something else. But now, in this case, I'm going to make it simple. So we are going to prepare the dynamical patterns for ordinary differential equations. In other words, like we are going to have like some kind of like a continuity in this. So more precisely, what we see on real number line is a continuum, something that we call a continuum. So in other words, like it is the connectedness together with like let's say the completeness of real number set. So without going further into the details of the structure of R and how can we generalize it in terms of a time set, or how can we have a different time sets included in that. Let's try to do this. Let's assume that our time set is going to be R in this case, and then I'm trying to relax it later. Let's see. And then M is none other than, now according to that structure, as I mentioned, even the textbook is not giving a really good, rigorous foundation for set M right at the beginning. So we are going to call it an arbitrary non-empty set, which is going to be indicated or identified as a state space or phase space. Why do we have like two different terms here? Phase space is in particular crafted for two-dimensional structures, where you can have in the space what you're going to have, like each point on that space will indicate uh, the position and the speed. So this is very much relevant to physics motivations, like when you try to describe the dynamics of particles, like oh, whenever you can have this the dynamics based on the position and velocity. I mean, not all cases will comply with this scenario. There could be, like, even in physics, there are situations where you cannot measure both the position and the velocity at the same time. However, this idea is motivated mostly by a two-dimensional structure. But even if you call it in general, that's not going to make it any harm. On the other hand, when you consider state space is much more general form of it. Like for any dimensional case, you can say the state space. So that simply means if you consider like 10 dimensional, I mean, structure, it's going to be like, even if you identify it like velocity, position, or something else together with some other coordinates, even in that case, you can just make it like state space. So if you see this terminology, it's simply, I mean, just interchangeable terms, but state space is much more general scenario, general in the context. So background information. I mean, these are the things that you do not need to worry too much, but I'm just giving you that background because when we work with this, you will see at a certain point minor details why it is going to matter, like why this terminology would be necessary. All right. And then the third set, it's a collection of transformations. Now, the third set is a collection of transformation from M to M. In other words, that is the meaning of transformation also. However, there is a little bit of consideration that we need to have carefully, right? Usually, when we consider transformations, right here, I just underlined it. Transformations. The thing is, when you consider transformations, in general, we consider transformations in like in a form like it's already a one-to-one correspondence from that set to itself. So it is going to be one-to-one and onto. Or at least you need to have one-to-one property, injective property. But now in this setting, I am not assuming that, and yet I am saying like it is a function. These GTs are just functions from M to M, where t varies. T is the indicator or the index for each function, and I'm calling them transformations without referring to this one-to-one property. You will see in a moment why we are doing it. Actually, in the last lecture, when we had that conversation, we proved the one-to-one property or the injective property of that function. So should we prove that? Should we not have it as a blanket assumption to begin with? Let me give you a little bit of context here, then you will see it better. So simply, the collection F is none other than a collection of functions from M to M. That is all I am going to say. And then a quick fact about these notations, like look at this, G superscripts T, G super T, or like GT, just call it GT, right? If you consider this function, now, what is this notation? At a certain point, you will feel like this is not the best notation to work with. There are different ways, there are more efficient ways of describing this, but for now, let's say G is the generic indicator for these functions, just like using F for a function, right? And then you can have different index. G1 is one function, something, I do not know what that function means here. So some kind of a function, G 1.5 is a possibility, G negative 3 is a possibility, and like G any real number, put any real number in that position, like negative pi or any rational, irrational, or uh, transcendental number, anything, right? Anything on real number, you can just put it there and it's going to give a new notation. So don't make it a big deal. Just try to identify G will stay there as a part of that symbol no matter what. And T is the one who's going to call a new function, right? So simple uh, notational facts to avoid any ambiguities. And then let's try to understand the purpose of G of T, or what we are trying to do with the G of T. In this way, when we clarify what we need G of T to be, that can pretty much give the entire background for this function. And when we have that background, perhaps we will be able to get more information about these functions. Now look at this. The first property. First of all, the first property, it is kind of like, it is not even a property. I'm just trying to give this function a name. These transformations, I'm trying to give some kind of a name. I should not be calling them transformations at this point. Let's call them mappings, right? So these mappings, GT, all right? So let's call them T advanced mapping. So T is indicating the time variable, and T advanced mapping, simply what it does is, if you apply GT to any element, GT of X, where X is an element of M, this is going to indicate exactly where it's going to land starting from X. Starting from X, that means at the beginning it's at X, and then when you apply GT on that element, it's going to be like have a jump to where it's going to be after T number of units. So this is exactly what I mentioned in the second point. Because of that, other than writing down something separately, let's have a picture. Something, a picture that can describe things very quickly. First of all, we have point X somewhere. Don't forget, this is the world of M, the space M. So we have dynamics based on these elements. So we start from a certain point, and then if we apply GT, let's use a different color. Yep. So I'm applying GT. Of course, it's going to be T advanced mapping. What it does is giving a new point, GTX, and that's going to be exactly what's going to happen to point X after T number of units under this, whatever this dynamical pattern that we are going to define. So that's the first step. And then, all right, so that's exactly what you can see here. If you see this, right? The second statement is exactly that. So the new state after time T, advancement. So now, all right, so this is the first observation, or first level that we need to have. The second part that we need is like, for this scenario, we need to have some kind of a consistency in this dynamical pattern. So that simply means it's like this. There should be consistency in terms of the way that we're going to proceed with. Now let's think about doing it like this. Somebody decides to start from point X and to spend t units of time. So it is basically using GT and get to this endpoint. So that is the destination. However, then they decide again, like, okay, starting from this point onwards, let's jump again. Let's have another jump to another point, but in this case I'm going to have, like, let's say a different time measure, or different, oops, Let me indicate it like this, G of S. So it's going to be like S units. So in other words, now your immediate initial point in this consideration is exactly your terminal point in the previous step. So it's going to be GTX. That's where you're going to start with GTX. And then you're going to apply GS to that. So now this is the simple story, right? Whichever the point that we prefer, right? So in this case, like where we start from is going to determine where we are going to end up with when you apply the corresponding advancement function, advanced mapping. Now, let's think about this for a moment. If this is going to define a dynamical pattern for consistency, this is what we need. Even if you do this, or if you decide, like let's say, to go from X all the way directly to that point, that should be the same action. So in other words, if you decide to go with G S plus T instead, let me make it G T plus S instead. If you do this, oh no, actually G S plus T would be the better option in that case. S plus T. If we decide this, it should have the same action, because if you decide like not to stop at all, so we are pretty much going directly. So it is not going to be this kind of like a path, like don't confuse yourself with that path. So it's going to be exactly this path, but it's not going to have a stop. We're not going to have any artificial stop. So we are going to go smoothly, we are going to proceed, and then we will start with X and we will end up with this endpoint. Now, if that is the point, if that is the case, there's one simple uh, point that we can see immediately, right? So the first property, or like the first observation that, not the simplest observation, the first observation for consistency is going to be this. If you consider G T plus S, and if you apply it to X, that should be same as G of S G of T X. In other words, if you consider the right hand side in terms of function composition, this is just the composition, right? And at the same time, if you think little further, it shouldn't matter if you measure t at the beginning or s at the beginning. T plus s is same as s plus t. In the time set, or we call it a group, we will see that word in a moment. So the collection of real numbers, the set of real numbers, is a commutative group under addition, and it is in fact a field. So we are going to have this simple commutative property in the time domain, in the time, and then you should be able to extend it simply to this. So the property that you're going to have should be not only this should be same as G T compose GS as well. But why is this important? Try to understand, when you consider function composition, commutative property is not something that comes at a low cost. Usually it is not going to work. You can find very trivial examples, like sometimes some counter examples require a little bit of work. In this case, like you can just uh, find that kind of a counter example while you're sleepwalking. So it is that uh, it is that frequent where you can fail this commutative property. However, in this case, we are imposing that condition as a natural condition on this. because that's exactly what we need to describe this dynamic. So try to understand whatever the structure that you're going to get at the end out of this is going to have something, a rich structure. Even without worrying about the structure of set M, what kind of structure we can impose on that, we are going to have something very structured in terms of T, or collection of these GTs, the collection of mappings, GT mappings. All right, so let's do this. Let's try to write down a couple of desired properties for GT. Now, you can do this me saying much about it, because the second property is exactly what we have written down. And the first property is, if you start from a certain point and if you advance by 0 units of time, that means you're not moving, right? So what would you expect? The natural should be X itself, right? It is none other than the identity mapping. So one can say this simple observation in this form. G0 is going to be, of course, it's a mapping from M to M. It is none other than the identity function. And then the second condition is exactly what all the forms that we had. This is going to be GT compose GS of X, same as GS compose GT X. Or by muting this X all along, you can say it's going to be just exactly a property of the functions, right? So in other words, in simple words, you're going to see this one. This is going to be GT. Even if you use this symbol like the composition, or like, let's say, when we work with it, when we know the context, sometimes we try to do this by muting. Just simple, like just have it like a multiplication notation. That is exactly what you can find in the textbook. It's indicated like just dot in between, but that is not a multiplication, that is the composition, right? Even if you indicate it in that way, try to understand the context, right? So this is going to be, now, the interesting fact is this property, the second property, actually the first one is called identity. Of course, you see the reason. The second one is consistency. In dynamical system setting, we just indicate these properties. However, now, once you have these properties, now you can see the background. And with this background, you do have a nice way of looking at the collection of these GTs, right? So about these functions. Now that is exactly where we had the first observation the other day. The first observation, right, let me have like 3 observations together. The first observation, okay, let's reveal them one step at a time. The first one is this structure, the collection F. This is none other than the collection of GTs, where T coming from the real number collection, right, near real number set. So this set, together with the function composition, you can just indicate it by just a dot. You're going to see this particular algebraic structure is going to be a group. Now, some of us may not have the background of abstract algebra to know what a group means. So I will give that idea briefly here. Wait for that in the upcoming couple of minutes. But for now, whatever it says, what it says is it's a algebraic structure. This is going to prepare a certain very useful type of an algebraic structure. And then it is not only that structure, it has some kind of an adjective, commutative. We know the meaning of commutative. Commutative simply means exactly what we have seen right here. The order of the composition would not matter. You can interchange the order of the composition. It's going to do the same thing. So it is a very rich demand actually. It is going to provide more structure into this system. So the first property is this one, the first one. So let's have a quick conversation about groups, and then based on that, the second and the third observations that I'm going to have will be the second observation is exactly the injective property of the mappings living in this collection F. In other words, every GT for any given T is going to give a one-to-one or injective mapping. And then every such mapping is going to be onto as well. So if you prepare, if you have these two are exactly the properties for transformations. Or like you can make a transformation uh, more general by saying like just one-to-one. So this is going to be a well structured. So it is going to be this is the collection of bijective functions on this. So the real deal here is based on the conditions that we impose for this, or based on property number one or proposition number one, you're going to have these implications, proposition number two and number three. So let's see this first. Step number one. Let me move these two results away from our work area until we may need to revisit in a moment. So let's look at these two in a moment. And we had already seen like the one-to-one property in a way, so the proof is going to be pretty similar for that scenario. But before getting to that, now, what is a group? Just in case if you have not seen the definition of a group would be like this. Definition, I'm just giving you this definition just to make it self-contained. And another comment about this, like when it comes to Arnold's book, when it comes to the consideration of groups, sometimes the discussion is not like that precise or like rigorous. They say like, oh, group is like a uh, structure, fancy structure that we are going to prepare. No, without saying that, let's make it exactly what it is. In that way, when you learn it, you can map it directly. So a group is going to be this kind of an algebraic structure. So G and G is an unempty set. So this structure is going to be called a group if we have these properties. The first one, the first property, I should not say it even as a property. So let's say G is non-empty, or I can start by saying like a non-empty set together with an operation and so on, right? The first condition, if G is non-empty, I will indicate it like 0, right? Yeah, let's call it 0. And then the first property. Now, this operation is binary. If it is a binary operation, if we say that word right at the beginning, we may not need to write this first property, but I'm just trying to make it pretty inclusive here. So this operation will this operation will have two operands from G. So in other words, it is going to be a mapping from again like G cross G again to G. So that is the story, but I'm going to say it in a different way. So for every AB in G, whenever you operate elements in B under this fancy whatever the operation, it's going to be inside that group or inside that set again. So this property is called closure. Of course, you can see why it is called closure. When you operate two elements, it's not going to go outside of that space. So this term is hidden inside binary operations without saying it explicitly. And then the second property is going to be for every A, B, and C coming from G. Now, when you have three elements, there's always a meaningful question that you should ask. How can you operate all three elements? You're not going to operate all three of them together. It would not make sense. If it would make sense, first of all, you need to make sure that it would make sense. So first of all, you're going to operate two elements. Let's say you're going to do B times T, B times C, operate B and C according to this order, right? You cannot switch the order unless you know commutativity. And then the result that you get for B operated with C is now operated with A. So that is the meaning of this whole thing. So for consistency of this one, or like let's say the more precise word is associativity, we are going to have A times B and then times C. It should be the same thing. So it simply means the order of these operations would not matter in terms of how you're going to group them. Which operation would be the first and then the next one, as far as they follow the order. Do you see like A, B, and C, A, B, and C? It's going to be the same outcome. So this property is called associativity. In fact, let me have the titles right here. This is the closure, and this is called associative property, associativity. And then the third property is an important one. I mean, most of these are important, but which ones are really important for our work? Let's think about that. The third property is there is a universal element living in this set such that when you apply this universal element, I call it E, right? So when you apply it oh, no, I messed up here. So I need to correct it. Look at this. This should not be for all right at the beginning. So let me have the correction in red color and then I will mark it. So this doesn't make sense. I should say there exists a universal element. That's what I said, but I did not write it. So let me write it precisely. There exists a universal element E. I'm just calling it universal because it's not depending on any other element. So that every element coming from this G, you can just call it G or like let's say any element, right? E times G equals G times E. Either way you can apply this, operate these elements, both of them will land on the same value, same number, same outcome as just the G. So in other words, the action of this universal element is not making any change to the other element that you're operating it with. So it doesn't really matter which order you're going to do it, you're going to have it like this. So this element, this universal element is playing the role of an identity. It's not going to change things. So this is called the identity. the existence of the identity or the identity property. And then the fourth property is going to be the inversion. So it sounds like this. Now don't forget, in property number 3, we guaranteed, if this is going to be a group, we guaranteed the existence of an identity. And now it is universal. So in the fourth property, this is what you're going to say. For every G belongs to this collection G, I'm using G, but you can use A, B, anything you prefer, right? So there is a, for any given element G, there exists an element depending on the choice of G. I will name it G bar because it's a different element, but it's depending on G also. So I wanted to have that inheritance somehow showed in this combination. So depending on G, there's a G bar, a different element. Need not to be different. Sometimes the element itself could be its own inverse. We have all of these possibilities, but look at this. This is what we have. For every G, there is a G bar in this way. G applied to G bar is going to be G bar applied to G. Again, you have the commutative property on these operations, even if the whole structure is not commutative. And then the action of this new element is to neutralize whatever the element G. So neutralize simply means it's bringing it back to the identity. So the action is none other than the inversion. I did not write it properly. Let me see. Inverse, right? So this is what we call a group. And these four properties are called group axioms. Or in other words, the basic assumptions for a group. If there is a group, I mean, a group is not going to be just a non-empty set. Always when you say a non-empty set, together with what operation, you need to specify that. Sometimes from the context when it is obvious what that operation is, we are not going to write it. We are going to say like, let G be a group. But we all know that operation should be there in the context. All right. So this is what we call a group. The structure G non-empty set, any non-empty set. I mean, it could be even cats and dogs if there is a way that you can operate them. I, I'm not going to make it too generic out of the mathematical spaces, but try to understand any set, right? Uh, as far as you can just have that binary operation or the operation defined on G satisfying these four properties, then we are going to call it a group. And this is an essential um, foundational pillar that you see in abstract algebra. If you have seen it, this story is pretty boring, I know. But if you have not seen it, keep it in mind, because when you see it in the next time, you will be able to match the story that you have right at the beginning of this conversation to that scenario. And then the next step. Together with this, there is an additional condition that you have here. The fifth property is not included in group definition. It is going to be a somewhat enhanced version of a group. If we have for every A, B belongs to G, for every two elements, if we have A operated B is same as B operated A, that simply means you have the commutative property no matter what you're going to operate with. Of course, we have the commutative property when it comes to the identity and the inversions. Like these are like very specific ones. But when it comes to this property with any element, this is called commutative property. So this is an additional condition. In fact, when it comes to a commutative group, We have a different name. We call them abelian groups, uh, courtesy of Henrik Abel, who was an unsung hero in the story of abstract algebra. Just go ahead and check that, look it up. You will be fascinated by the history of Abel. And one interesting fact about that is, like, when you write an abelian group, usually you just simply say like abelian group like this in a writing. You're going to just say it like abelian group, like here Abel. uh, Abelian group is not like this A is not even a capital letter. Usually when we refer to a name, we do have a capitalization, right? Some kind of like a name. Now, uh, Abel is so embedded in algebra in a way that the name is not considered like with that capitalization. So it is an even bigger honor, in my opinion. Uh, all right. So abelian group is a commutative group. So now, why am I saying it? Look at this. Our group here is an abelian group, or simply wait until that comes from algebra. For now, you can say these two commutative group, right? It's a commutative group. Now, given that we have seen the definition or the background of groups, right? Since we have seen that, let's bring this part separately. I'll copy and let's proceed to a separate page. And let me just edit here. All right, so our starting step was like this proposition, right? We started describing this proposition, and then we wanted to describe what a group means. That is how we had that whole deviation from this proposition. Now, if you go ahead and think about like this setup, do this. You can have a proof. Try to construct that proof. But what's behind this proof is not even a proof. What you're going to see is pretty much uh, this the construction already getting aligned with the properties of groups. Why do I say so? Other than saying the proof, I'm going to say the outline of the proof. All we need to do is to identify these pieces, right? First of all, we need to make sure that F, this collection of mappings from M to M, is not going to be empty. The collection of mappings, right? So this collection is not going to be empty due to one reason. It is not by the way that we wrote it. It's not going to say much, because that collection, I mean, like if we wrote it like saying, if we write it in this form, I mean, these functions could be anything. Even who can make sure like there is no function included in this at all? We cannot say. That's exactly where we need to go back and check what we demanded this collection to be. Don't forget, we ask the desired properties of GT. The first one is G0 is supposed to be something called the identity. It should not change where you are because you are having zero advancing. So it's going to be just that point itself. So it's going to be the identity. right? So this is the starting step. So now, without going back and forth, look at this. We have the identity right here, and that identity is going to play exactly the role of the identity of that group. And the second part is, because of the existence of this identity, you do have non-emptiness of this set to begin with. There is at least one element that you can consider. And then the next part is, when you try to prepare the product structure for this group, it's none other than what you're seeing here, right? Or more precisely like this. If you put the composition in between, it is going to be abelian or commutative because of this side, right? GT composed with GS is same as GS composed with GT. So this is exactly what it is. Here what we call consistency is exactly the key to prepare this group structure. All right, so in that sense, if we just get to this, let's say, I mean, without saying much, I would say this F is non-empty, um, since G0 belongs to G0 equals identity, right? So this is the identity mapping that belongs to this. There is at least one single element in there. And then, of course, this is a binary operation, right? So the first property, I should not say much because GT, you get two elements and you're going to operate them. GT, GS, right? If you say more precisely, you should say like name like two elements from this collection, and then they have this form, they inherit this form. Therefore, you start by calling them GT and GS, but I will just make it like a little bit of hand waving here, assuming that you can work with the details. So right here, what you're seeing is exactly this property. Now look at this. If you compose them, what you're going to get is another member sitting inside the same collection, GT plus S. This is another function sitting inside F. So this belongs to this. And this is going to work for any function GT and GS coming from this collection, right? So this is going to prove as closure. And then when it comes to the second property, GT, GS, and GR, if you call it like that, right? You can just, I mean, this operation, the way of operating is going to give you exactly what it's going to happen, right? What's going to happen here. So GT and then GS plus R right here, and then you apply it, it's going to be G of T plus S plus R, and then the associativity would occur right here. So it's going to be, in fact, it's going to seem like this, and then that turns out to be, which is going to be decomposed to G T plus S, and then this is broken by, right? Work with the details, but that is the simple plot. What is the identity? We know the identity, right? So the simple scenario here is you consider any GT, any element from that collection, which will inherit this form, and you're going to just operate G0. That is going to be just the same thing as GS T. I'm not going to say much about this because this is pretty obvious, right? And obvious is kind of like a very much like an underrated term. If you're not seeing why it is obvious, I mean, this should be obvious, but if you're not seeing it, that's exactly the meaning is like you need to work with that so that you can see it obviously, right? So this is not complicated. So the next one, the inverse. All right, this is the good one. Uh, Wait for it. So for any given t, now what we need is this. We need to come back to this identity. Identity is none other than G0. To work with that, this is what we need, right? For any given gt, I need to operate it with something so that I'm going to land on G0. What would that be? Don't forget, we are trying to play with these indices, right? So this is supposed to be just none other than G minus T, right? Now look at this. This is interesting. What we see here is T advancement, T advance, you advance by T units, and then you advance by negative T units. So in other words, what you're doing is you reverse time. You can consider backward trajectory. If you know exactly how to proceed forward, there is an assumption in this setup where you can go backwards and figure out where you came from, right? So in other words, you can reverse a trajectory. Now, of course, now in this case, according to this setup, yeah, of course, this is a real number, right? We do have it. So it's going to work perfectly. So look at this. If you look at these four properties, this is exactly what we call a group, right? And as an additional advantage of the structure that we defined here, we do have the commutative property according to the way that we proposed it, right? So recall that property. The commutative property was right at the beginning. All right, so it is going to be a commutative group. So that's exactly how you can establish this fact. And this is the outline. You can just work with the details. The proof is not exactly the thing. The important part is like proof is going to sometimes some proofs are not just about like doing just the proof. I mean, one can work with the details and one can do a proof. But this is going to be sometimes interesting to see what is natural and what we are demanding. And is it what's going on? We can analyze it when we do a proof. So this proof is giving us a very nice couple of scenarios, so couple of scenarios or something, right? Uh, Up to this point, everything is fine, but look at this. The key points, key takeaways are, first of all, we need to have like this kind of like, there should be an identity that makes sense. There should be like this associativity. This is a natural property. If you just have like two stops and you can, I mean, if you consider the path or the advancement in three different stages, it should give you the same outcome no matter what. And then these properties are pretty evident. In fact, like this one is by construction and this one is a natural property. Natural, but that is what we demand in this. However, not all groups or not all dynamical systems will have this time reversal property. We can look at some examples little later when we proceed with the lessons and when we just get familiar with some types of differential equations, I can show you a quick couple of examples where the negative trajectory, the backward trajectory is not a possibility. So what it says is this. In our work, when we try to prepare this background, we try to go with not with the best general form. The best general form will not have a group structure. Instead, it will have something called a semi-group structure, where we are going to have the first two properties guaranteed. Only for a semi-group, you're going to get the first two properties, associativity together with the closure. And then the third property with the identity, I mean, this is also natural for our case, so it is an added advantage, but this one becomes really tricky. So the last one is going to be the reversal of time is going to be a tricky ask. So with this, I'm trying to give you some generalization. So now this is the important thing. It is very important that you understand. Uh, I'm trying to prepare this playground, but I'm trying to have some kind of like a motivation also without, uh, hopefully without not overwhelming you. Because I'm going to I'm going to use some of these different pathways later to have further generalizations, but for that, we need to wait until we get to that point. But right now, I'm telling you, we are going to get to that point. All right. So now, for now, if we sit back and recap exactly what we've done for a moment, this structure is going to be a commutative group, right? And so for now, don't worry about semi-groups or like not being able to reverse the time or this G, oh, this G of negative T is not forbidden for our consideration in the first half of this work. So feel free to have it whenever needed. Now, look at this. Here, based on these properties, actually, I mean, we did this work uh, right here. We considered that it's going to be a one-to-one mapping. F is every mapping inside Fn, F, in other words, Gn, any mapping, particular mapping is going to be one-to-one. And don't forget, we considered that from like, again, each mapping is from M to M. And you can further prove that it's going to be onto M2. So if we consider this one, this is nothing other than the collection that you see here is none other than the collection of bijections from M to M. So now, the other day in the first lesson, we had a brief proof for this. Actually, we worked with the outline, almost all the steps were there, but I did not provide you the background with what's happening in a group, and those group properties are exactly what would guarantee what we are working with, what we worked with in proposition number 2. So this is why I am just bringing it up here. Now, since you have those group properties and since you know exactly those structures, the way that G, GT, and GS would be worked with each other, now you can go ahead and provide the proofs of these two. In fact, like when I provide the assignment in parallel to this lecture, I will add these two as, I mean, in a way that you can just work with it. Right? So I'm not planning to give any further intuition, anything about this at this point, like just try to prove them, right? Proof, consider it as exercise. All right, so let's proceed. Mm, right. Right. So that is the background of the story. And now with this, since we got to know the background related to this collection F, and now we can simply call it a group of transformation. It's going to be a group first of all, and without any problem, I can call it transformations now. It's going to be one to one, and not only one to one, it's going to be on to. And at the same time, each function gt is depending on one parameter. So it's called a one parameter group of transformation. And then M is none other than where we have all the dynamics defined on, like those are exactly the, I mean, that's exactly the collection of points. It need not to be exactly the positions. It's going to be positions together with speed, right? So it is the phase space. It is about the state, right? So phase space indicated by M, and F is going to indicate we are already familiar with that, right? One parameter group. So in the forthcoming work, sometimes without saying this, especially in the textbook also, it's preferred writing the set just like GT with curly brackets around just to indicate it is a collection. So you can do that. So we can use uh, this symbol, I mean, to indicate the collection of one parameter group of transformations without any problem. If you see it in that way, just try to understand it's what we are looking at. And then the phase flow is, I mean, think about this. You're considering phase space, together with some kind of an advanced T-advanced map collection. So what you're trying to do is to define some kind of a flow on that. So it is called the phase flow. Now this is the terminology. So what you can identify is this is where it is happening. This is how it is happening, right? So when you put them together, it becomes exactly the process, the flow, right? So now the next step. Uh, Again, here, now, since we do have like two um, different editions, right? In edition number one of the book, which gets to the rigorous kind of like presentation very quickly, and in that we get to these definitions very fast. On the other hand, in edition number three, you're going to see it with a little bit of time. It's going to take a little further. But now you can find the idea of, like, let's say we're going to define something called motion. What do we mean by a motion? Now, simply, for any given point, for any point on M, you're going to define a mapping, right? Now, what you're trying to do is this. In the previous case, you were looking at like starting from a certain point, you can think about the advancement, right? You can see like how to advance by t number of time units. Now you're going to do something different. Now you're going to start from a point and you're going to consider all possible t advancements, right? if you do this, can you see you can have a map or you can have a function defined on top of variable t. So in that case, what you're going to fix is your starting point or one point along the way. We can simply say this is a starting point, the initial condition. So in this way, right, without thinking much, let's define it. Define function, I mean, in this case, like we define it like phi, right? So it's going to be from R to M, defined by like the phi x of t is none other than the evaluation of x under mapping of gt. But look at this. Now, when you vary time t, you're going to vary not only t here, you're going to vary this entire mapping, t advanced mapping. So if you just think about this, we are going to have a proposition, but before getting to a proposition, let's have a picture for this. So what are we going to have? So here's M and here's X. And what T advanced mapping doing is for each and every time, right, it should give like if you consider T let's say G1 or something, it should tell us after 1 unit where it should be. And then from that point onwards, if you have another time advancement, it's going to tell us how far it should be. So if you consider different time advancements, what's happening is like you're going to define something along, right? Look at this. If you consider any point, you can say like how much, like what kind of advancement would bring you to that point. So this is none other than defining a trajectory through point X. So that is exactly what we're trying to do with this mapping. And of course, it makes sense to call it the motion, right? Motion is none other than um, exactly it's a trajectory. It's a trajectory, but make sure you understand this function really well. When you indicate this function phi x on this domain, what you're going to get is not like what's going to happen for each and every value of t. What you're going to get is something like phi x is there, and through that there is some kind of a trajectory. And if you look at this function itself, you cannot say at which point it's going to be, which time, you cannot say much. It's going to be like so it's going to be just kind of a trajectory that you're going to see. And if you need to see what's happening with time, you need to extend this to another dimension. Let's wait for that. Now, the simple housekeeping stuff that we need to have behind this definition. First of all, we call it the motion. All right, call it the motion. Does it make sense? Because cannot we have like more than single motion through a certain point? Cannot we have one motion like phi x and then another motion going through this one, call it like psi x? Cannot we have that kind of a setup? How is it guaranteed that we are not going to have two different versions, two different motions? So according to this statement, when we say like it's called the motion, maybe a better way of saying that it's called a motion. And then if you after establishing the uniqueness, you're going to get the fact that it's going to be, in fact, unique. It's the motion, right? And that is the first part. And then the second one, it is called the motion of a point. Now, this phrase was taken directly from the way it's presented in the textbook. but I wanted to say a little further, right? So I do not find it is really natural to call it motion of point x. Instead, like, let's call it motion through point x, because point x is not actually moving anywhere. It is somewhere, and then through that there is some kind of a path, right? So that is what we can see. And then, so all of this is happening under the action of the phase flow of m. M simply means where it's happening. F is simply how it's happening, the flow, right? So this is exactly the story, right? Now, what can we do based on this? So the proposition 3, let me make sure that right. Yeah. Before going further, let's have one proposition here. Proposition. I guess we had three propositions already, so we can name it like proposition number 4. At a certain point, we will lose this numbering. Until then, I will keep it up. So the next one is for every x um, there is one and only one motion. I will call it motion through, motion passing through x. Of course, you need to say passing through x. I will just simply have a full stop there, but you need to say generally under what? Under the phase flow of MF. Since it's clear from the context, I am not going to say much. So look at this. I am saying here this one is going to give you this new function that you define is going to be unique. But now, this is exactly what I mentioned earlier, like when I drew that picture, right? I put two different trajectories and say like, oh, how can you make sure? Now, how can you really make sure? Now, this is what I'm going to do. Think about this. Good point to ponder. Proof. Think for now. And let's have it as a part of our uh, first assignment so that you can play with it and see. Now, the interesting thing about some of this is like when we prepare this background, when you prepare this kind of a structure, sometimes this uniqueness. I mean, since already you have seen one-to-one property of function g, a function g superscript t, right? gt is one-to-one. Is it related to this scenario? Can you see the connection? Sometimes some of these proofs or some of these propositions are not like something really fancy. It is just about like you're looking at it in one direction, and if you turn it around and see it in the other direction, the whole story is like the whole observation is right there. But either way, we list it as a result because this is interesting. What we're trying to say is like if we try to now, no, the closest thing that we are going to see for a solution of a differential equation is this structure. Now we are getting close to where we should be. What we are trying to do is not to define the differential equation. What we're trying to do is to define what kind of a solution it can have, right? So these solutions or the dynamics of that setting will lift this differential equation out of it. But of course, like it is not the natural thing, right? When we consider differential equation, it should come the other way. But what we're trying to do is to identify that general background in that setting. This is what the best thing that we can have for a solution. There's an initial condition and there is a mapping progressing in terms of t. There's a function progressing in terms of variable t. That is exactly the solution of an ordinary differential equation given in terms of t. So can you see we are getting close? Now, in this case, like this particular map f phi x is going to be unique, right? That is what this proposition says. Now think why, right? So it need not to be a complicated proof if you look at, if you go ahead and just check through exactly what we've been doing, right? So it is about like rotating this because we had like these two dimensions, two directions to consider: variability of x, variability of t. So we can think about these two together. All right. So expect that as a part of our first assignment, where we are actually going to have a little bit of practical way to see, right? So now the next step is this. Now, earlier when I drew this, I said, I mean, this is exactly the picture that I drew early. Do you remember, like I drew M and I said like along X, you're going to have, like when you consider this phi, the way it's presented, represented is like something like this. Through this, it will go in the forward direction and backward direction. It's going to be like this. Oh, it need not to be like this in particular. It could be just like a closed loop. It could be a spiral, something. I mean, there are many things that you can have, like some kind of a trajectory or a path on this. And that is exactly what you say, like when it comes to the image set. When you consider the image set, now this is the image set, in fact, right? The best way to identify that kind of a function is like to look at what's really happening on this curve, right? So this curve, this entire curve, which is this image set, is called the phase curve on the phase space. This is living in the phase space, and it is the phase curve passing through X. And then point to ponder how these curves appear on M. Of course, that is exactly what we just described. I mean, there is nothing to ponder here. You can just think about the way that it's going to appear. All right, so let me make sure the next step. All right, great. All right, I guess we are in a good shape to add more little bit of, I mean, add little bit of structure. Uh, Before going further, now, let's summarize exactly what we've done up to this point. I told you we're trying to prepare like the formal structure to define dynamics, right? So now we did a couple of things. We started with set T or set R, where the time variable is just moving along R. And then you have the phase space or the state space, which is given by M. And then we had like two different functions or two different collections of functions. One mapping is GTs, the collection of GTs. The other mapping is, by the end, we define the motion. Now, if one is like little curious, if you're thinking about like, okay, wait a minute. Are we doing this in the most efficient way? Cannot we have like different symbol, different way to write this down? Of course we have. Let me provide that uh, structure little bit here, and it is used frequently in dynamical systems. But I'm just going to show you these symbols. Even the symbols are not pretty uniform, like you can have different ways. Sometimes like some symbols are going to be helpful over the others when it comes to different applications. Now, the first step, look at the time set. The time set here, I indicated it by T. I said it is going to be T, and the T can be R. It can be R. That is exactly what we considered, right? Or it can be R plus. If it is R plus, look at this. Now I'm just avoiding the negative direction of it. There are no negative values that I can include. So if that is the case, I can just have positive additions along. Look at that. That is a scenario that I described earlier. It's not going to be a group structure. Instead, it's going to be what we call a semi-group structure. So for now, let's hold that, right? Let's not deep dive into that. Or one can say like this dynamical structure need not to be just like a continuum. It can be like jumping from one point to another. If you consider Z, or in other words, the collection of all integers, even including zero and negatives, right? In that case, you can go the forward jumps or backward jumps. Now, the time measurement is going to be given by integer values. T equals 1, T equals 2, T equals 3, and T equals -1. That means like you're going jumping backwards one time, right? Likewise. And if you associate the same thing with like only the natural numbers, that's going to be the positive direction of those discrete jumps. So there is a world of dynamical systems where we are going to describe discrete dynamics. You're not going to define it on a continuum. Instead, you're going to define it with these discrete, I mean, with the gaps. All of these are included if you just simply generalize your definition a little bit by putting a t as a time variable, or depending on the application, if you're going to say that, what it's going to be. However, in our work, at least right at the beginning, our work is going to be just only R. So do not overthink about all possible scenarios. In a study of dynamical systems, you're going to see the rest. And then when you consider R plus, these two, anything related to R, I mean, both of these are in the domain of differential equations. We can have it in the domain of differential equations, but we are not going to have these two as interesting scenarios in our case, because we cannot have the discrete increment, discrete evolution described by differential equation. So we are going to be playing with real number set or positive real numbers depending on what scenario it's going to be, and the state space, I mean M, is well known. You're familiar with that. And then the next one is the interesting one. Earlier you had two different pieces, GT, mapping GT, and the motion. Now I'm just bringing both of them to one single mapping, one single function called the flow map or evolution rule. If you think about this function, it has both of these measurements. If you consider it, at which time, at what initial input you're going to have, or starting from which condition you're going to have the advancement. Or in other words, at which time, at which point. So if I can define that, pretty much like everything is described, right? So that is exactly what you're going to see in this scenario. So uh, the starting point together with the advancement will map to another point. So it is going to define its evolution naturally. And then the identity. This is the same thing as saying G0 X is X. It's just the same thing. We are not calling it G anymore, right? And then the second property, the consistency, go ahead and check what we wrote there. It is about a composition. Think about it, how it's going to match with this. So the purpose of this function is exactly to have like where it's starting from and what kind of an increment that you're going to spend to get to this overall outcome. What is the end point? So if you think about it in that sense, go ahead and see. We used the idea of consistency before, but consistency in this form, it is just the same thing. Think about it. And this is how we look at this evolution rule or flow map in dynamical systems, which is going to be pretty much the same thing. And at a certain point, the textbook uses the same, but it is not the same way it is presented, right? So I wanted to give you that just in case if you're wondering whether this is, I mean, how this is working in the setting, right? So the next step. I guess since we're preparing the background and at the same time we have a little bit of background already for some uh, of this structure, let me put one on top of that so that we can uh, have the conversation targeted to our next step. So look at this. Mm, all right. Just to identify exactly what's happening here, right? Now, interesting fact. When it comes to the textbook and the approach, like the way that it is presented, like we're going to work with this the preparation to a point where we are going to forget what actually we are working with, differential equations, right? Uh, we are not in a position to see differential equations yet, apparently, because we have not talked about at least one single differential equation yet. But yet, let me provide, like, let's say, one or two other properties on top of this so that we can have more structure into this, right? So I'm going to add one more proposition on top of this. I would like to see, now this is proposition, I guess, number 5. The reason behind this proposition is basically like I know now before writing, let's try to have some intuition. If you consider X, and if you consider like the motion true, or like let's say the phase curve true X, this is none other than phi X of R. It is going to be the phase curve. It is going to be like pretty much like. Now, this structure is going to give us like a very good intuition for the generalization later when we talk about manifolds, right? But for now, you can just look at it in this way, right? There is something. And then uh, if we consider another trajectory true. Okay, let's call this x1, and let's call another point x2 completely different from x1. It could be anything else, right? True that you're going to have again another curve. Now you should ask a question. Wait a minute. I mean, should you have these solutions in this form? Cannot they cannot you have these phase curves intersecting each other? When I drew this second one, or like let's say let's draw a third one. X3 right here. So cannot I have this kind of a possibility? This is going through this and then it's intersecting this like one point. Now use your intuition. Think about this. Can this happen? Think about in terms of what we're trying to prepare here as well, right? If it is not consistent now we need to think about um, according to exactly what makes sense in this case, right? So if this is going to happen, think about this. These are two solutions or two trajectories. If they happen to be in one place, like if there is like one point in common, you should be able to reverse it under certain uh, timing, and you should be able to go back, right, to locate where it was. But now if you're on this kind of like an interesting point, now if you try to reverse it, or even if you try to go forward, now there is an ambiguity. Should you proceed the let's have color blue for this? Should you go through blue or should we go through pink, right? But I mean, can you see the point vaguely? All right. So if you see this issue a little bit, now the formal way of preparing this background, actually this is not mentioned in the text, but this is the cleaner way of saying it. So let me give you proposition number 5. The proposition number 5 will give us, this is what I'm saying. Let the relation I'm going to define a relation be defined on M. Okay, what is a relation? What is a relation on M? So you're going to have some kind of like you're going to associate two elements, right? The relation is going to give the truth value if they're related. It's going to be just like you can have an indicator function on top of that if needed. So either they are related or they are not related. So, and this is what I'm going to say. Like, my expectation is you all are familiar with equivalence relations. So let a relation, this relation be defined on M by this, by X related to Y if and only if phi X equals, phi X evaluated at T equals Y. Let's prepare a little, let's have a little bit of background. A little bit of space here. for some t belongs to R, let's do this. Let's make it a little more formal, right? By saying defined by M by this relation for xy sitting in M. X is related to y if and only if phi x t is going to be y. So what is happening is this. This is a trajectory or a phase curve, right? So I'm going to say these two phase curves are related. I mean, these 2 points on M are related if they are on the same phase curve. But I'm going to be a little more specific. I'm going to say you start from X and you have the T advancement, so that after T units, you're going to meet point Y. So I am simply not saying that you can just, I mean, you cannot switch X and Y in this case, right? This is the starting point, this is the end point. So X is related to Y if this is the starting point and this is the end point uh, under some time, right? For some time. I'm not specifying what that time should be. So if you have this relation, you can prove that this is going to be this relation, this is called tilde, right? That's a symbol. Mm, or simply called X is related to Y, something like that, right? So don't make things too complicated. Let's say prove that this relation is going to be an equivalence relation. Equivalence relation. On when you talk about an equivalence relation, of course, we know we need to start with a relation from one set to itself, right? So equivalence relation on M. So if it is an equivalence relation, there will be an interesting scenario. Every equivalence relation is going to define a beautiful picture on whatever the set that we consider. The whole point behind an equivalence relation is to break that set, in this case set M, into a partition structure. So you're going to have a partition of that set. So which is going to be just like this. You're going to have bunch of phase curves, and these phase curves together will compose that set M. And if you consider these phase curves, can they intersect each other? If they intersect each other, they should be the same phase curves. So in other words, they cannot have just like non-trivial intersections. If they intersect, they're going to be the same. So this structure is going to give you a better picture of what we are trying to do, what structures we are preparing here. When you consider these phase curves, you're going to get like, we will see multiple scenarios. No examples yet. The purpose of not having examples is to have this dense uh, presentation just to prepare the background. And then we can follow specific examples to see some visualization. I mean, to have some visualizations. It is going to be with us pretty soon. But for now, I guess this is enough for this session, given that we have a couple of things that we can work out. And at the same time, on next session, I'm planning to proceed with like a little further with a few more technical definitions. However, on the next session, I'm confident that we can go towards the introduction to differential equations based on this scenario. So, based on this background. So, you will see the assignments corresponding to the corresponding assignments added on the communication methods, like either on Piazza or like a direct way with the group communication group, or um, so definitely when it comes to have to have the conversations, we will conduct it through Piazza so that I can have your submissions, and then we can have like the work graded back. All right, so that's exactly going to be the conclusion of this session, and let's meet on the next one. And we're getting closer to talking about differential equations. See you soon. Bye.